If you push a magnet into a coil of wire, why does a current suddenly appear? And why does it vanish the second you stop? Let me tell you about Faraday's discovery. Early 1800s, Michael Faraday and his buddy Henry discovered something interesting. A changing magnetic field can create a current, even without a battery. This is called electromagnetic induction. The key word is a changing magnetic field. If it's a steady magnetic field, it doesn't do anything. But if it increases, decreases, or reverses, then what you get is an induced current. Let me visualize this for you. So this is what Faraday set up. He had an iron ring, and wrapped around it on one side was a wire connected to a battery, but it had a switch. So it's connected to the battery, and on the other side, wrapped on the same iron ring, he had another coil, but there was no battery. It was connected to what's called a galvanometer, which tells you the current. Now this battery over here, when switched on, it creates a magnetic field. How does that affect the current? When he switched the battery on and the magnetic field appeared, the galvanometer jumps, it detects a spike in current. But when it's switched off, it jumps again, but in the opposite direction. So turning it on, current gets detected. Turning it off, current gets detected. But when your battery is left on and steady, what he found was that there was nothing, no current. What this experiment tells us is that a constant magnetic field does nothing. A changing magnetic field induces current. Let me give you some key vocabulary. First is induced EMF. Induced EMF is the voltage that appears due to a changing magnetic field. Induced current is the current that flows because of this EMF. And magnetic flux, which if you remember from Gauss's law, represented with this symbol, it's the total electric field that passes through a loop. Here's the golden rule. A changing magnetic field is what causes EMF, which means if there's no change in your electric field, then there is no current, since the current is coming from the EMF. Let's break down what happens when you move a magnet near a coil. So say we have a galvanometer again, telling us the amount of current. And plugged into this, we got a loop of wire. There's going to be 3 stages that we're looking at. First is we move our magnet up through this loop. So the field might look something like this, the magnetic field. And what's happening here is when it gets pushed in, the magnetic field be inside of this coil space, it increases. This change in the magnetic field induces an EMF, and an EMF creates a current. So the current begins to flow through our wire. This is the first scenario where we push it up through. What if we pull our magnet out of the loop? So we take it out. What happens now is the magnetic field decreases because it's no longer within the coil. The current is still flowing, but now it's in the opposite direction, like that. And the needle on the galvanometer will deflect the other way. This is the second scenario. The first one, we pushed it through this hole. Second one, we took it out and we moved it down. What if we just held it steady inside? What happens with the current? So we know that if we push it up through, current goes one way. And if we move it down, then the current switches. It's with the magnetic field increasing and decreasing. And if we hold it steady, just right here, like this, no moving up or down. What's happening now is the current going through this loop of wire, it's constant. And since it's constant, there's no EMF that's induced, which means that there is no current. And by the way, it doesn't matter if you move the magnet or the coil. As long as the field going through the loop is changing, you get current. It's the relative motion that matters.